Hello, this paper is going to take you through the 2021 A-Level Computer Science exam paper for Unit 1 Computer Systems. Question 1. OCR Insurance uses a computer system to calculate the price that customers pay for car insurance. The computer system contains a CPU, GPU, RAM and ROM. State two factors that affect the performance of a CPU. This is quite a straightforward question. So it's GCSE level, so there is clock speed, and the other features you could say are the number of cores, or you could always say cache as well. Part 2. Explain the difference between RAM and ROM, including how these are used by the computer system. Okay, again, quite a GCSE type of question. First of all, I would start off by saying RAM is volatile, ROM is non-volatile. Okay, then let's talk about what they do. So RAM stores data and instructions for programs that are currently open, for example, the operating system. And ROM stores the boot up instructions. You could just say the BIOS. Part 3. Describe one non-graphical use OCR Insurance may have for the GPU. So the graphics processing unit. So the whole idea of that is that actually it's going to be used to process data, but it'll be focused on, or process, you could say data or instructions, but it's going to be the more complex ones. So if you think about it, the fact that GPUs are used in Bitcoin mining is that kind of a principle. So a GPU complex instructions and data. Then we need to give an example. So this is where you have to really apply it to the scenario. So they've specified in the question OCR Insurance. So 2 marks, so we need to relate it to the scenario always. So we could say, for example, modelling. We could say modelling, and we could say modelling expected outcomes. Part B. The CPU uses pipelining to improve efficiency. Explain what is meant by the term pipelining. Now, this is a bit of a tricky question because pipelining appears on the Unit 1 and Unit 2 spec, but the definitions vary slightly. Now, on Unit 2, it's that the output of one process becomes the input of another. However, where it appears in the Unit 1 spec, it's really referring to the CPU. So we need to think of it in terms of the CPU process, and that's talking about the fact that while one instruction is being executed, the next one is being decoded, and one before that is being fetched. So that's what we need to be discussing in this question, and it's all relative to where it appears on the spec. So because this is a Unit 1 paper, we're going to go with the Unit 1 definition, which is all about concurrent processing. So we could say that instructions can be concurrently processed. Okay, and then let's just explain it. Let's give some examples. So it's just what I was talking about earlier. So we could say while one instruction being executed, and it's best to start from executed and work your way back. The next is being decoded, and the next one fetched. Okay, so we've got 2 points there for a 3-mark question. So what else can we say? We could talk about potentially the issues that could happen. So you could say if there's a branch, the instructions being fetched and decoded might be might be unnecessary, so the pipeline needs to be flushed. There we go. Part C. OCR Insurance's computer system uses secondary storage across the company in servers, client machines, and for backup purposes. For each of these, discuss whether magnetic storage or solid state storage would be most suitable, taking into consideration the advantages and disadvantages of both. So this is just a discussion between magnetic storage or solid state storage. Because it's one of the long essay questions and it's worth, how much is it worth? 9 marks. What we need to do is we need to demonstrate our knowledge, apply it to the scenario of OCR Insurance, and then evaluate and make a decision as to what would be best for them. So first of all, what we can do is we can define what magnetic storage is. And we can explain that it's a disk, or it's a disk in terms of a hard drive, but it's a magnetic surface which has a head which goes across it, and then it will raise or lower the surface depending on whether it's a 1 or a 0. Okay, and then what we're going to do is we're going to just talk about the different characteristics, and this even dates back to when you would have been doing GCSE. So we can talk about the speed, the cost, reliability, durability. I'm going to do those two the other way around because they're very similar. Speed, cost, reliability, durability, capacity. Good, so we're going to talk about those different features. Obviously, I'm just going to write in notes, you will go into more detail. So you can say it's a reasonable speed, not as fast as solid state. And obviously, we've mentioned solid state now, so maybe you want to actually do the solid state bit beforehand because there's a bit of a comparison here. Very cheap per gigabyte. Durability, it has moving parts, so it's more easily damaged, so it can be damaged. Reliability, it can be quite reliable, but as we said before, it's got moving parts. Not the most durable. Capacity, and we'll just say it's infinite. Okay, good. So you're going to explain those obviously in more detail. So when it comes to the reliability and when it comes to all of this, we can apply it more to the scenario. But I'm just going to go through the knowledge part to begin with. Okay. So then we're going to go to solid state. Okay, and we can explain it's a storage device which is made up of transistors. They can be set to 1 or 0 dependent on data. Oh, we missed portability. Let's add portability. Not portable, not very portable because of the moving parts. Okay, and obviously we'll talk about the fact that actually if it's being used for some of these purposes, then it's going to be static. But for now, we'll just leave it. Although you do have magnetic tapes, don't you? Sorry, So solid state next. So we've defined it, now we've got to talk about the characteristics. So speed, cost, durability, reliability, capacity, and portability. So speed, we can say it's very fast. Why is it very fast? Because it's made up of transistors. Cost, it's quite expensive. Durability, very durable because there are no moving parts. Reliability, it's very reliable. Capacity, large but not infinite like magnetic storage. And portability, very portable because of its durability, and it can change. It can vary in size. Okay, so that's all of our knowledge done. Now what we need to do is we need to relate them to the scenario. Okay, so the scenario is that it's for OCR insurance, and they use it in servers, client machines, and backup purposes. Okay, so looking at this, other than potentially backup purposes, it's not going to be used for carrying data. It doesn't need to be portable. They're going to need lots of space, presumably. What else is there we can take from this? Speed potentially will be important, but not of the utmost. Okay, so let's go through magnetic. Again, I'm writing these in 3 different sections. You could always do it in one. So you could talk about magnetic, your knowledge, and as you talk about your knowledge, you could talk about your application and your evaluation. But I'm just doing it in 3 different sections. So magnetic, and let's just talk about it. So we could say speed wouldn't necessarily be important for backups because you could leave that to happen over time. But in terms of the servers and the client machines, speed would be of the utmost importance. So they'll need to be working. They'll need to be working. It is not important for the backups. Because they can be done over time. Cost, because they're a big company, they want to keep they will have because they're a company, they'll be looking to keep costs down. OCR insurance. Durability. Even though there are no moving parts, it's not expected that we could do durability and portability actually together. And because there are no moving parts, because the data will not be transferred, physically transferred, it will not need to be portable. which means it'll be quite durable. Or the durability is irrelevant. And in terms of reliability, because it's not being moved, it will be reliable enough. Good. Capacity. Infinite storage will mean they can store all they want. Now we'll do the same thing for solid state. Okay, so we could talk about the speed. The fast speed will mean that staff can get on with their work because the client machines will be faster and the servers will be faster. Client machines. Operate well, enabling people to get their work done, staff to get their work done. Okay. Next up, we've got cost. We just said that the high cost will be a disadvantage. Yep. There's nothing else to say. Durability and portability. So we could say, again, we're not expecting the data to be transferred. So even though it is more durable and portable, we don't get the full benefit of that. Even though the is durable and portable, they will not transferring the devices. Good. And then once we've done that one, we are going to move on to reliability. They will want a reliable device to store their backups. And capacity. We could say even though it's not infinite, it should be large enough to store their data, all of their data. And we could reference the fact that a lot of companies use solid state for big data, so it should be suitable for a smaller company. Okay, so what we've done, we've demonstrated our knowledge, we've demonstrated our application, we've given, and what we need to do is now we need to evaluate it, and we need to make sure we give some good examples in this. Okay, so that's the one thing we need to make sure we do. It's always good examples. So we're going to conclude, and I would actually say that either would be suitable. I could say dependent on budget, I would recommend magnetic. If budget is not really an issue, go for solid state. So both devices would be suitable. And just because of space, I'm just going to write it in shorter sentences. Dependent on budget, go for magnetic. If no money is solid state. And then we can give an example. We can say this means that staff will be staff's PCs will work faster. And then we can say they'll be able to get more work done. However, they'll still be able to work at a decent pace with magnetic. So make sure you're always giving your examples. You could potentially give more examples in the knowledge and application section as well. Part D. Customers' details are stored in a flat file database table. Customer. An extract of the table is shown below. So we've got a table with customer ID, surname, title, phone, car reg, and all of the relevant pieces of data. Part 1. State what is meant by the term primary key, identifying the primary key in the table. So quite straightforward. A primary key is a unique piece of data used to identify a record. Okay, the second part of the question is identify the primary key in the table above, which is going to be customer ID. It's the only piece of data that will definitely be unique 100%, because you might have two people with the same name. We've got two people with the same titles. You might have two people who live at the same address or have the same telephone number. For some reason, you might have the same car registered on there twice. And also customer ID is underlined, which generally means it's the primary key. Customer ID is primary key. Part 2. Write an SQL statement that would show only the customer ID and surname fields for customers with the title Miss or Mrs. So when we do an SQL statement, we always have select first, and then we have from, and then where. You'd have order by if we're sorting it, but it doesn't ask for that. So we need to select customer ID. And the way that we do two is we do a comma and surname. We're going to get them from the table called customer. It's just written there. Just check it's customer single. Yep, it's not a plural. And where, and we want it where the title equals Miss. And because it's a string, we need to have it in speech marks. And we've got a second condition. So we've got title equals Miss or Mrs. So we're going to say or. And we don't do or Mrs. We would do title equals Mrs. Mrs. Like so. Part 3. Describe one problem that would arise with a flat file database structure if a customer wanted to insure more than one car at the same time. So actually that's what we're discussing here. You might have the same car in here, and the issue is you're going to have duplicates. Duplicates are redundant data, which means it's wasting space. So this would result in duplicate information being unnecessarily stored. This would take up more space. Good. So we've covered the duplicate data, and we can get the key term in there, data redundancy. So we say this would result in data redundancy. Good. So we've got about 3 points in there for a 2-mark question. Part 4. Describe how the flat file database structure could be altered to efficiently allow each customer to insure multiple cars at the same time. You may assume each car is insured to only one customer. Okay, so how could we improve this database? So just having a look at this, what we would need to do is we'd need to split it into 2 tables. So we'd have a customer table with all the customer details, then we'd have a car table with the car details. We haven't got any car details here, but we could add them, and we could say that car reg would become the primary key. And then what we would do is we would add the customer ID, the primary key from the customer table, to the car table as a foreign key. And then we'd create a one-to-many relationship saying that one customer could insure many cars. So let's just go through it first of all. So the table could be split into 2 tables, one with the customer details. So we could say no car reg, just to be a bit clearer, and another with the car details. This would have the car reg as the primary key, and store any additional information about the car itself. For example, make and model. So we're applying it to the scenario. The car table would take the what's it called? It was called customer ID, primary key from the customer table, and use that as a foreign key to indicate which customer corresponds with the relevant car reg. This would require a one-to-many relationship stating that one customer can insure many cars. Question 2. Convert the denary number 231 to an unsigned 8-bit binary number. So it says it's unsigned, so there's no 2's complement, no mantissa or anything. It's just like what you'd have done at GCSE. So we have to write 231 in 8-bit binary. So we're going to get an Excel sheet up, and our number we're going to be dealing with is 231, and we're going to just draw a table to help us. Okay, and what we do is we're going to just quickly go through each one, and we're going to just do each column one by one. So first of all, does 128 go into 231? Yes, it does, so we put a 1 in there. Now we need to figure out what number that we are dealing with, and the remainder will be 103. So now we're going to do, does 64 go into 103? Yes, it does, and our remainder is going to be 39. Does 32 go into 39? Yes, it does. I should have changed that to 39, sorry. It does, and that's going to give us a remainder of 7. Does 16 go into 7? No, it doesn't, so we put a 0. Does 8 go into 7? No, it doesn't. Does 4 go into 7? Yes, it does, and it gives us a remainder of 3. Does 2 go into 3? Yes, it does. It gives us a remainder of 1. Does 1 go into 1? Yes, it does. So that's our answer to the question. so we can put that in. It's a 1 mark question. I'd put the working out on there. I don't think you'll get any marks for the working out on this, but I would put the working out on there anyway. Part 2, convert the hexadecimal number 6F to an unsigned 8-bit binary number. So it's going to be unsigned again. So we've got 6 and F, and we need to convert each one of those. So 6 is the equivalent of 6, F is the equivalent of 15. So we'll put 15 there. Okay, so what we can do is we can use this same table. It's only hexadecimal, the highest number is 15. There's only 4 bits. So I'm just going to take you through the process of this. It's quite straightforward. You can do it without the table. I'm just going to do it for argument's sake. 8 does not go into 16. 4 goes into 16 and it gives us a remainder of 2. 2 goes into 2, gives us a remainder of 0. So the 6 would be 0, 1, 1, 0. Okay, it's just taking my zeros off there, so I'm going to just quickly fix that. So 0, 1, 1, 0. Okay, and now 15. The way I remember it, 15 is the highest number that you can represent, so that's going to be all of the ones, so it's going to be 1, 1, 1, 1, but let's just work through it again. So 8 goes into 15, it gives us a remainder of 7. 4 goes into 7, it gives us a remainder of 3. 2 goes into 3, it gives us a remainder of 1. 1 goes into 1, and there we go. So our answer would be like that. Now what we need to do is we need to join the two numbers together. I think this is going to get rid of my 0 again at the beginning, but it's going to be 0, 1, 1, 0, 1, 1, 1, 1. And that would be our answer which we would put in. So if we go back, put that into here. Again, it's a 1 mark question, so I'm presuming just the answer alone is fine. It doesn't say to show you're working out, but I'd be tempted to put it in anyway. Part B, the floating point number, and we've got a number, is stored using 6 bits for the mantissa and 4 bits for the exponent, both in 2's complement. So we're working in 2's complement now. The number is not normalized. So a normalized number begins with 0, 1 or 1, 0. Give the normalized version of this number, show you're working out. So what we need to do is we need to figure out what the number is and put all of our decimal points in, etc. So let's take this number and we're going to just put it into our Excel sheet. This is my working out, obviously. So what I would suggest you do is when you do your working out, you're going to do it on the paper. You can do it on a piece of paper and then just attach it. Absolutely up to you. So we've got 0, 0, 1, 1. 0, 1. So that's our mantissa, and our exponent is 0, 1, 0, 0. Okay, so that's our number. I've just forgotten what we're trying to do. We're trying to give the normalized version of this number. Okay, so we're just trying to write it in a normalized version, and we're going to show our working out as well, because it's not normalized because it begins with 0, 0 rather than 0, 1. Okay, so let's write this number out, our mantissa. Okay, and let's figure out where our decimal point goes. So 0, 1, 0, 0 is 4. You've got a 1, you've got no 1, no 2, but you've got a 4. So the decimal point will go 1, 2, 3, 4. So it goes here just before the 1. So this is our number, okay? Our final answer has to be 6-bit. We need to bear that in mind. Now, because it's normalized, it has to begin 0, 1. So what we're going to do is we're going to get rid of the unnecessary zeros at the beginning, so the duplicate ones. So we can get rid of this one, but we're going to keep this one because now it begins 0, 1. What we need to do is we need it to be 6 bits. So we've got 1, 2, 3, 4, 5. So we're going to just put an extra 0 at the end. Now we need to figure out what our new exponent would be. So the decimal point moves over 1, 2, 3 times. Okay, so what we're going to do is we are going to set our exponent to 3. Okay, and the way you would write that would be it's going to be 4 bits, I believe the question specified, didn't it? Yep, 4 bits. And it's 2's complement we have to remember. So because it's 2's complement, you're going to have the negatives. So it's going to ultimately be 0, 0, 1, 1. Like that. So that's our exponent. And our mantissa will be this number without the decimal point. So our answer would be 0, 1, 1, 0, 1, 0. And then we've got our next bit, which is the exponent. So that's our answer. Put that in. And obviously you'd have your working out on there. Part 2. Convert your answer to part 1 to denary, showing your working. So what you can do is you can actually use your working out from part 1. I'm going to go through it from, just as though we didn't have that working out to use. So we've got our answer. And what we're going to do, let's write out the mantissa. So we've got 0, 1, 1, 0, 1, 0. And we need to put our decimal point in. It goes over 3, so it's going to be 1, 2, 3. And, oops, full stop, not a 1. And what we're going to do is we're going to just add our weightings on top. So it'll be 1, 2, 4. And because it's in 2's complement, that'll be -8. Now, when we look at it going this way, so with the exception of the first one, actually it halves each time. So we're going to go from 1 to 0.5 to 0.25. And we're going to just add them up like normal. So we've got a 4, we've got a 2, and we've got a 0.5 on there. And we add them together, that's going to give you 6.5. And that's our answer. So obviously you would include all of that working out on here. I'm just putting the actual answer down because my working out is on a different sheet. Part C, add together the 2 numbers below. Both numbers are stored in normalized floating point format using 6 bits for their mantissa and 4 bits for their exponent, which are both in 2's complement. Show the result in the same format. Okay, so what we're adding to do here is we're adding numbers, which is quite straightforward, but they are 2 floating point numbers. So what I would suggest we do first of all is we write them out with the decimal points, because I think that will make things a lot easier. So let's write them out first of all. Let's get rid of this. So our first number is 0, 1, 1. And our exponent is 0, 1, 1. And it's not got my 0 on there at the beginning, but we'll just bear that in mind. There should be a 0 there. And the second number is 0, 101. And the exponent is 0, 1, 0, 0. Okay, so that's got rid of the 0 as well. So both of these have zeros at the beginning. So this exponent would be the equivalent of, so we haven't got a 1, we've got a 2 and a 4, so that's 6. And this one would be 4. So let's put our decimal point in. So so we start off here and go 1, 2, 3, 4. Okay, and we've reached the end, so it's going to be 5, 6. So it's moving over 2 places. So what we're going to do is we're going to add on some extra bits and then add our decimal. So one more time, it's 1, 2, 3, 4, 5, 6, like so. And let's just double check that. 1, 2, 3, 4, 5. Oh, I missed one. 6. It should be here. So I'm going to put my decimal point in there and change that into a 0. I'm just going to, you know what, I'm just going to check this one more time. 1, 2, 3, 4, 5, 6. Yeah, so my decimal point's here. And my next one is 4. So we go 1, 2, 3, 4. So my decimal point will go here. So I'm going to just move this over. And there we go. So that's our two numbers that we now need to add together. So what we have to do now is we need to line them up. So what we're going to do is we want to get the decimal point lined up the same. That's the key thing. There we go. So there's our number. And what we're going to do now is we're going to just start to add everything up, and then we'll figure out our experiment. So we've got 0 plus nothing, which gives you 0. Decimal point there. 0 plus nothing, 0. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 1, 1, 0. Okay, so here is our number. Let's just push that down a bit. And what we need to do now is we need to get it to, I believe it was 6 bits, wasn't it? Let's just go back. Yep, 6 bits for the mantissa. So we've got 1, 2, 3, 4, 5, 6. So we can get rid of the one at the end, but we're going to just leave that for now. I'm going to just figure out where the decimal point goes. So it's going to go over 1, 2, 3, 4, 5, 6. So my exponent is going to be 6. I'll just change that to text, which is going to be written as 0, 1, 1, 0. So that is now my mantissa. I can get rid of this on here. Sorry, that's my exponent. I can get rid of that on there. Now I need to cut this down to be a 6-bit number. So 1, 2, 3, 4, 5, 5, 6. And I've just got a 0 at the end here, so I can get rid of that, because when you expand it, I'll just put zeros in place. So here is my answers. 0, 1, 1, 1, 0, 1, and I've got 0, 1, 1, 0 for my exponent. Again, you would want to put in all of your working out. I've done it on an Excel spreadsheet, so I haven't, so you do it straight on the page. You could do it on another piece of paper and always attach it if you like. Question 3. A website sells tickets for sporting events. The website uses HTML and CSS and JavaScript. Describe the purpose of HTML and CSS within the website. Okay, so HTML is used to to generate the content of the website and the structure, okay? We could also mention the fact that it uses tags. And give an example. We could do title tag. And let's just put in the close one just in case. Okay, so we've got an example, we've got a definition, good. And then the same thing for CSS. So we could talk about the fact that CSS defines the appearance of the website. It sets things like fonts, sets formatting, and we can say it can be embedded into the HTML or in an external file. Part B. One page in the website contains a hyperlink on an image. When the image stored as ticket.png is clicked, the user is hyperlinked to the page booking.htm. Write the HTML code to implement this hyperlink. Okay, so all we're looking to do really is we're going to try, when a user clicks on ticket.png, it takes them to booking.htm. So what we need is we need to be able to insert a hyperlink, and within that hyperlink we need to be able to insert an image. So to insert a hyperlink, we're going to use the A tag, and when we open a tag we also close it, Now, when we do the A tag, we don't just do A, we do href. Most of the time we use href rather than just the href attribute rather than just A on its own. So the hyperlinks reference is going to be booking.htm, which is just here. We'll do it in speech marks because it's a string. Okay, make sure we do HTM and not HTML. Okay. So we've got our link there, and what would happen is we've got that close bracket, and in here we would normally write our text. So we'd say click here to book or something like that. But we're not going to have any text, we're going to have an image. So we need to put in the code for an image. So that's going to be the img tag, and we're going to have the src attribute, and the source of the image is ticket.png. There we go. I split mine onto 3 lines. You could do it all in one if you liked, but that's just an easy way to think about it. You could do it on a different piece of paper and then write it up nice and neat. And I'm missing my close bracket there. There we go. And then write it up nice and neat all as one if you'd like. Part C. The website charges a booking fee of $2.99 on each ticket sold. In addition, if the tickets are purchased from outside of the UK, £4.99 is added to the booking fee. The booking fee is calculated using JavaScript, a function called booking fee. Complete the definition of booking fee function below. So what we've got here is we've got the function. So we've got function booking fee, it's just a declaration. We've got num tickets, I'm presuming is number of tickets, and country. They're the parameters which are given in. Then we there's a variable called non-UK price, which is $4.99. So I guess that's a variable saying how much it costs for a non-UK price. Variable price per ticket, written up here, price per ticket is $2.99. I'm going to write 2.99, no pound sign on there at all. Variable total is 0 at the moment, okay. If the country is not the UK, so if we're not the UK, the total is the total plus. So if we're outside the UK, we're going to add $4.99. We're not going to write $4.99, then we're going to use this variable. So we're going to add on non-UK price. Good. And the total equals the total. So it's going to either be 0 or $4.99 based on if they're in the UK or not, plus something multiplied by the price per ticket. That's going to be the number of tickets. So we're going to take the 0 if they're in the UK, or $2.99 if they're outside of the UK, and we're going to add that onto the number of tickets multiplied by the price per ticket. Then at the end of the function, we need to output something. We're not going to print it, we're going to return it. Part B. The JavaScript function above is used to show the users the booking fee. When users click to buy tickets, the booking fee is calculated again on the server. Explain why server-side processing is used to recalculate the booking fee. Okay, so what's happened is it's been calculated on the user's computer, but then when they actually do the final booking, it's done on server-side processing. So the question is, why is it really there? Why are they going to the effort of calculating it all again, and why are they doing it on their servers? Okay, so I think the first thing is you want to make sure it's accurate, because if it's being calculated on the user's computer, they could potentially change it so that it comes up as less. So we could say that client-side processing can be changed. By the client. Okay. This way they make sure that the booking fee is correct. Have more control. Good, okay. And also there's facts of, for example, the client's browser might have scripting turned off. So there's some people turn off JavaScript to protect themselves. disabled, even better. And it just needs to be accurate, dependent, regardless of the location. Part 2. Explain one advantage of client-side processing to either the customer buying the tickets or to the company who own the websites. So an advantage to either party. Okay, I would say an advantage to the client is that it's less load on their servers. And that means that they've got more bandwidth available. There's lots of different things you could say. So you could say if it's done client side, then the client's going to get a faster response really, because they don't need to send data to and from the server. But this is the one that I would choose to go for. Part E. Users are able to search for and find the ticket website using a search engine. Search engines can use indexing and ranking. Describe how a website is indexed by a search engine. So this is basically saying, how does a website such as Google get its list of websites? So the first thing is that they have software called a spider. So a spider will start at an initial page, okay? So a spider starts at an initial page. And then that spider is going to go through the website and record all the information, such as the text and meta tags. This will go through the page and record all the information, such as text and meta tags. Okay. And then what it also does is it records the position of each word within the page. It records the position of each word within the page. And it stores them using an index. And what it does then is it will follow the links to any other pages that there are. So it stores them using indexes, and that's kind of indexing that you would have in an array, similar to that, like a pointer kind of thing. And then it stores any links on the page, and then does the same to all of those links. And we've got a bit of a cycle, so you start off with one page and it just keeps adding to it over and over again. A search engine can use PageRank algorithm to determine a website's ranking. The PageRank algorithm utilizes a dampening factor. State what is meant by a dampening factor. A dampening factor is basically, it's a value which is between 0 and 1, and that's used to predict the probability that a user will not actually follow through the link. So, value. Okay, so just because it's on there and it's linked, it's got all of the links going in, etc., doesn't mean someone's necessarily going to click it. So we have that as a dampening factor to give us a bit more of a reality check. Give two other factors that affect the output value given by the PageRank algorithm for the website. So first of all, we've got the number of links coming into that page. And secondly, it's going to be the PageRank value of the link of those links coming into the page. Or say, instead of saying coming in, we'll say linking into. So just because you've got loads of links, that's one thing, but the value of those links affects the factor that's output. The Computer Misuse Act means that computer users are criminalised for simply trying to learn how systems work. Discuss whether or not you agree with this statement. Okay, so first of all, we need to explain our knowledge. So that's knowledge about the Computer Misuse Act. So we can say what the purpose of it is. Okay, so that's all about preventing unauthorised access to computer systems. And again, I'm writing in note form, but you'd have to write a bit more detailed. We can mention the three main factors. So the first one is accessing a computer system or unauthorized access to a computer system. The second would be unauthorized access to a computer system with the intent to make any changes. The third would be unauthorized access to a computer system and making changes. Okay, so that's our knowledge. Okay, obviously you need to put it into a bit more detail. And then what we need to do is we need to kind of apply it. We haven't got a full scenario, so we can always make up something. We can give some kind of scenario of our own, okay? So we can say that actually people can still investigate how computer systems work. They just need authorization. So users can investigate how computer systems work. They just so then we could give a hypothetical example. You could ask for permission from the computer system owner, or set up a system for investigation, for example, a virtual computer. Okay, so we're explaining the different knowledge and applying it. We could talk about things like how we could break it. So we've given an example because this needs to be a balanced argument, remember? So we've said a way that we can overcome this. Now, how can it be broken? So a way it could be broken, it could be broken by accessing someone's email account without their permission. So the key thing in this is that we're actually presenting a balanced argument. So you might have your own opinions, but we have to present a balanced argument. And then at the end, in the conclusion, you might want to justify what you think, because what it's asked us to do is to discuss, and we're going to have to do it. We can't just put one side in there. Ultimately, we need to make sure that people are aware of the law. Ultimately. And then what we're going to do is we're going to move on, and we've got our conclusion next. And we can say this is where your kind of opinion comes in. But again, everything needs to be explained online. So we could say that users can learn about the Act from many sources online. Good. We could also go on to talk about and we kind of touched on this, we could say if you want to investigate, all you need is permission. Good. And a lot of the time that there are options to, you could say there are options to learn how to use these. And then what I've written here is actually very, it goes against what I've said. So I'd actually conclude by saying I disagree with this. So you can say there are many programs or systems to be able to investigate. So what I've written is generally come out on the disagreeing. So I'd say overall, I disagree with this statement. Question 5. All users of a computer system have a unique username and password. The computer system has implemented two-factor authentication so that users must respond to either an email or text message containing a secret code to be able to access the system. Let A be a Boolean value for if the user enters a valid username. B be a Boolean value for if the user enters a password that matches their username. C be a Boolean value for if a user is able to respond to an email containing a secret code. D be a Boolean value for if a user is able to respond to a text message containing a secret code. Q be a Boolean value for if entry to the computer system is allowed. Complete the Boolean expression below. So what we need to do is we need to take this equation. We've got our inputs A to D and Q is the output, and we need to put it into a Boolean expression. So let's see if we can understand this. So A is the username, B is the password, C is responding to an email, and D is responding to a text. So the way it works is that they enter their username and password, and if that's correct, then they have to respond to a text message or an email, then they get access to the system. So if we work first of all, they have to enter a username and password. The hint is actually there in the question. You have to enter your username and password quickly. So the username is A, and we're going to do and B for the password. So they have to enter the username and password. We're just going to put brackets around those. Once they have entered their username and password, we need to have an accurate email or text message. And again, in the question it's there, email or text message. So there's the big hint. So it's C for an email, or, and we're going to say D for a text message. Both of these conditions need to be met. It's not that they just do one or the other, it's both, so we're going to do an and. So it's A and B, and C or D. Part B. Another Boolean expression for a logic system is shown below. Q equals not A and not B. Simplify this Boolean expression so that it does not include any negation. You must explain which Boolean algebra rules you are using at each step. Okay, so what we're going to do is it's quite straightforward actually. If we have a look here, we've got negation, we've got a negative here, we've got a not here, and we're going to apply it to that one. So we can apply it to here, and we can apply it to here, and you're going to end up with two not symbols. So basically you're going to have not A and not B. So from that, what we can, once it's expanded, we can say actually we've got double negation here, and that's going to give us A and B, because what we can do with double negation, two negatives make a positive. Part C. The logic circuit above has two inputs, A, B, and two outputs, S, C. Give the Boolean expression for the outputs S and C. So what we have here is a half adder. We just need to do the Boolean expression. So we're starting with S. If we follow it backwards, we can see it goes into an XOR gate. So what I'm going to do is I'm going to first of all put my XOR symbol down. Now this should be underlined, it's just that I can't do it because of the computer I'm on, so it should be an underlined V. And my two inputs, if I follow them back, are A and B. So it's going to look like so, but there should be a line underneath the V, the OR symbol, so it's an XOR. And C, we're going to do the same thing. We've got, if we go back from C, we've got an AND, so I'm going to just put an AND symbol on there. and the inputs going into that are A and B. So we'll just put them in front, A and B. Complete the truth table for the logic circuit. Okay, so it's just the sum and carry really. So we've got 0 plus 0 gives you 0, carry 0. 0 plus 1 gives you 1, carry 0. 1 plus 0 gives you 1, carry 0. 1 plus 1 gives you 0, but carries over 1. Describe how the logic circuit can be adapted to add together two 4-bit numbers. So basically what the situation is here, we've got a half adder. A half adder allows you to add together two 1-bit numbers. The reason that it only allows you to add together 1-bit numbers is that there are two inputs. In this case it's A and B. They would be the 2 bits you're adding together, and you get a carry. However, when you move on to adding a second set of bits, you might have a carry coming in from the first 2 bits. So what needs to happen is that your system needs to be able to take, your circuit needs to be able to take a carry in as well. So that's why it needs to be updated to a full adder. So what we need to do is we need to describe the process for creating a full adder. So what we could do, we could start by saying a second half adder needs to be added. Okay, and we can explain this is by adding a XOR and an AND gate. We can move on and we can explain that the new one would also need, the adapted circuit would also need a carry in input. Good. And then we can explain that the input for the new XOR would be the carry in, and it would also be the sum from the original OR gate. Good. Okay, and then we can say the new AND gate would have the same, but I'm just going to write out the same thing. For the original XOR, okay, and just say in brackets the sum. Then we need to explain, because we're going to have two ANDs which are just sitting there not doing anything. Then we can say both AND gates would go into an OR gate. Good. And then we could say the output, well, we need to explain what the sum and the carry are. We could say the output from the new XOR gate is the sum. And we can say the output from the OR is the carry. Finished. Question 6. A program written using Little Man Computer instruction set is shown in figure 1. And then we've got a load of code in Little Man Computer. Various registers are used when the program above is executed. State what is meant by the term register. Okay, so that's simple. That's just a memory location used to store data, and it's quite fast. So we can say fast, then Explain how the accumulator is used when the line BRP pos is executed. So let's have a look. So there's pos. Okay, so we've got BRP. BRP stands for branch if positive. So what it's going to do, it's going to look to see if the value in the accumulator is positive. Okay, and sometimes it gets a bit confusing because is 0 positive or negative? We're going to count 0 as positive because there's no negative sign in front of it. So let's just specify. There. Part B. Complete the table below to show the outputs from the program given the inputs 12.5, 18.2, 16.4, 3.7. So we've got two inputs in each section, so I'm guessing there's two numbers to be entered. The first one will be the first and the second one will be the second. So let's have a quick look. So we've got our code here, and look, we've got num1, num2. So what I'm going to do, because we have to follow this code through, but we're going to use the numbers they've given us. So I'm going to just do num1 here, and I'm going to do num2, just so that I've got something to write it down so that I can follow it through. And what I want to do is I want to know what my outputs are. So we start off with the numbers 12 and 5. Okay, so input 1, input, and we're going to store 12. We're going to store it in num1, input, and we store it in num2. That's going to be 5, okay. Then we load num1 because 5 is currently in the accumulator, so we're going to put 12 in the accumulator, and we subtract num2, which is going to give us 12 minus 5, which gives us 7. Let's write that down so we remember. And we're not saving this anywhere, which is interesting. So it says branch if positive. It is positive, so we go down to pos, because it says pos here. And we're going to store this in num1. So that's 7 now. Sorry, that 7 now moves into num1. Load count, so we've got a variable called count, and count down here is set to 0. I'm going to just add count onto my table here. And it starts off as 0, and we add 1. 1 does have 1 in it, yep. And we store it in count, so count now equals 1. Branch to main. So we're going to go back to main. We're going to load num1. So we've got 7, so we'll put 7 in the accumulator. Subtract num2, which again is 5, so that's going to take us down to 2. Branch if positive, it is positive. So we're going to store this in num1. I've written it down there as though I had stored it, but we hadn't stored it, but now it's telling us to store it. We're going to load count. Count has 1. Add 1 to it and store it. So now because we're storing, that's going to be 2. Branch to main. We load num1, which is 2. We sub num2, which is 5. So that's going to give us -3. Hasn't said to store it yet, so it's going in the accumulator. And then it says branch if positive, but the accumulator has -3, which is negative. So that says so we don't go to this line, we go to the next one, and we're going to load count, which is 2, so the accumulator is going to have 2. And we're going to output it, so the first number we get outputted is 2. And then we load num1, which is 2 as well. Oh, and we're going to output it again, it's another 2. Where do we go from there? And then we halt, we stop. Okay, so looking at that, we were consistently subtracting number 2 from number 1, but we stopped when we hit a negative number. So that's ultimately division. So the first number, we've got the first 2 is going to be 12 divided by 5, which is 2. It goes into it twice. So we went through twice and we got that answer before we hit -3. And then what we did at the end was we gave the remainder. So what this program is doing, all it is dividing two numbers and then giving the remainder. So we can just use that logic now. So 18 divided by 2 gives you 9 with a remainder of 0. 16 divided by 4 gives you 4 with a remainder of 0. 3 divided by 7, 7 doesn't go into 3, so our output's going to be 0, but there will be a remainder of 3. write an algorithm using pseudocode that has the same functionality as the code in figure 1. So we're just going to write that in a high level language. So first of all, we need to get people to enter their numbers, and we're going to store them in variables called num1 and num2. So we'll say num1 equals, and we're going to say input, enter a number. And then we'll do the same for num2. Num2 equals input, enter a number. So we've entered num1 and num2, and now we just need to output the answer. So because for the first digit, we're just taking the whole number, aren't we, the integer. So we can use div. So we can just div it. So we could say print num1 div num2. So that's going to print our first digit, and then we want to print, now we want the remainder. To get the remainder we use mod. So we print num1 mod num2, and that's going to print for us the remainder. Part D. In assembly language, different modes of addressing memory can be used. Discuss the different modes used. You should include how the operand value is determined, what an operand of 27 would refer to in that mode, the reasons for requiring different modes of addressing. So what we're going to do is actually laid out quite well, because we have to do our knowledge, we have to do our application and our evaluation. So first of all, we want to do our knowledge, and our knowledge can be on the different modes of addressing. So we've got immediate, we've got direct, we've got indirect, and indexed. Okay. First of all, we can start off just by saying how the value is determined. So we can say an instruction will consist of two pieces of information: the OP code, which is the operation to be performed, and the operand, which is the actual value or address. So a command is actually an instruction, two pieces of information, the OP code, and we can give an example, and the operand which holds the data or address of the data. Okay, we can say there are four different addressing modes. Okay, so we've got immediate. So with immediate, this is the actual data to be used. So, for example, add 27 would add 27 to the value in the accumulator. Okay, direct, this holds the address of the data. Okay, and again, another example would add the data stored in memory bank 27 to the accumulator. Indirect, so this is a bit trickier to explain, but this holds the address of where the data is stored. The address of the address even. And then, for example, add 27 would add the value, stored in the address stored in memory bank 27. I'd actually explain that in a lot more detail. So I'd maybe say, for example, if 27, memory bank 27, stored the value 99, then it would add the data stored in 99. And finally, indexing, it holds the address, which is offset, so there'll be two figures using an index, so brackets, we can say like an array. The operand holds the address of the holds the address which is offset using an index register, like an array. So we could say there'll be, yes, it's just like an array. Okay, so we've done our knowledge and we've done a bit of application already because we've got all of our examples in there. The reasons for requiring multiple modes. So this is, why don't we just use one? So for example, immediate addressing, the size of data is limited by the size of the operand. And let's give an example. For example, if you want to add a, let's say 1000 bit number, you will be limited by the operand size. Okay, and then we can say with direct is also limited, e.g. you may have more memory banks than the operand allows you to enter. Okay, so we've done immediate, we've done direct. Indirect, okay, this requires more fetches. Good. And with immediate, it can just take longer as well. So not immediate, index. As the memory, location, and index need to be accessed. Okay, so that's how you write that one. Again, I've written notes, yours would be more detailed. Question 7. A business uses an array with an identifier, W names, to store workers' names. A variable with the identifier top is used to store the index of the last element to be added to the array, which is also the element which is next removed. And then we've got W names, we've got all of the indexes 0 to 6, we've got 5 employee names going from 0 to 4, and the top is pointing to 4, 4 being the last element to be added. Part A, state the name of the type of data structure described above. So what type of data structure is this? So if we have a look, it's got a pointer on there, okay? The pointer is called top. Let's see what else is there, a bit of a hint. It points to the top, obviously, which is where the data is added and where the element next will removed. So if you add something, it goes to the top of the data structure, and then when you remove it from the top as well. So basically that's a stack really, because it's first in, first out. Part 2. Using pseudocode, write an algorithm that allows the user to enter a name which is then pushed onto the data structure above, checking first that the data structure is not full. Okay, so first of all we need to get them to enter a name. It's quite straightforward. Name equals input, enter a name. Good. Enter a name which is then pushed onto the data stack above, checking if the data structure is full or not. So we need to check if it's full first of all. So the way we check it's full is there are 6 addresses in there and it points to the last one added. So how do we know if it's full? If it's on 5, that means that we've got space for one more. But if it's on 6, yes, if it goes up to 6, then we're not going to be able to add one. So what we can do is we can say if the pointer is less than 6, or clearer way would be if it's less than or equal to 5. So we could say if top is less than or equal to 5, then we want to add it. So we're going to say w names top equals name. So we'll say w names top equals name. And I guess, does it say what we do if it's not full? We'll just do an error message, else, and we can say the data structure is full. There we go. So we've entered the name, we have checked if it's full, we've added it, and we've got an error message. So we've got 1, 2, 3, 4 points for a 4-mark question. Part B, the same workers' names are stored in a binary search tree which is ordered alphabetically. Kirsty is set as the root node, with Martin, Louise, Alex and Anna added one by one. Part 1, complete the tree above to show where Martin, Louise, Alex and Anna would be added to the binary search tree. So it's quite simple. All we do is we take the names one by one in order. So we're going to start with Martin. We compare them to the item. If it's bigger, we go to the right. If it's smaller, we go to the left. So we're going to compare Martin and Kirsty. M comes after K in the alphabet, so we go to the right. Now we move on to Louise. So L comes after K in the alphabet, so we go to the right. Now we're on Martin. L comes before M in the alphabet, so we're going to go to the left. Next we've got Alex. A comes before K in the alphabet, so we're going to do Alex over here. Then we've got Anna. A comes before K, so we go to the left. And we've got A compared to A this time. So what we do is we move on to the second letter, L and N. And we can say that N comes after L in the alphabet, so we're going to do Anna here. And then we just draw the lines in to connect them together. Okay, moving on. Next question is, describe the process of using the binary search tree above to search for the name Zoe. So what we're going to do is we're going to just explain how we would find Zoe. So we're going to start at the root node, Kirsty. And we can just explain Zoe is bigger than Kirsty. So we move to the right. We check the right, we could say, check the node to the right. We could say Martin. Okay, so then we could say, we compare Martin and Zoe. We could say Zoe is bigger than Martin. So we check the node to the right. We could say there is no node to the right, so we can conclude that Zoe is not in the tree. Part 3. Compare the efficiency of a binary search tree to a linked list when searching for data. So we just managed to search for Zoe by only looking at 2 nodes rather than going through all of them. So actually what we can conclude is that a binary search tree is more efficient. And we've got to say why. It's because you don't have to check every item. There. Part 4. Compare the efficiency of a binary search tree to a hash table when searching for data. So it's similar to the other one, the last question, but actually we're just comparing it to a hash table rather than to, I think, was it a linked list that we did? Yeah, then a linked list. So we can actually say a hash table is more efficient. Is more efficient. Okay, we need to say why. This is because a hash table takes you straight to the location. You say the data reveals the memory location. Part C, an object-oriented system is implemented to organize further information about each worker's attendance. Classes, objects, methods, and attributes are used in this system. State the meaning of each of the following terms. An object. So an object is an instance made from the class. Good. A method is an action performed by the object, or an action that can be performed. And an attribute, you could say, is information or data. We could say brackets, a variable stored within the object. Part 2. Each worker has a name and an attendance figure which can be between 0 and 100. Write a definition for a fully encapsulated customer class providing both get and set methods for all attributes. You do not have to write the code for the constructor method. Okay, so we've got to make a class and it needs to be encapsulated, so all attributes need to be set to private. We need to do a get and set method for all attributes, and you do not have to write the constructor class. So let's do class, and what's the class going to be called? Does it say in the question? Okay, it doesn't specify, so we could just call it workers, I believe. Yeah, so it's just got the worker, each worker has a name, attendance figure. Okay, so let's call it workers. Okay, so we've got that bit done. And now we're in there, so we don't have to do the constructor, so we don't need to do new or anything to create it. We need to do the attributes. So we've got the name, and we're going to make that private. Good. And then after that we've got private, and we've got the attendance figure. So we've got those set. So we need to do a get for both and set. So let's do get, and it's going to be public, and because it's getting, it's going to return something, so it's going to be a function, public function get, and we're going to get the name. So we get name, open and close bracket, and that's just going to return name. And then we need to do the same for public function get attendance, and we are going to return attendance. Good, now we need to do the sets, so it's going to be public, and because we're setting, we're not returning anything, so it's a procedure, and we're going to call it set name, and we're going to need to take the name in as a parameter, so we'll call it worker name, and we're going to say name equals worker name. And now we're to do the exact same thing for attendance. However, if we look here, it says it has to be between 0 and 100. So we're going to need an if. We need to validate what they're putting in. So public procedure, and it will be set attendance, and then we'll do worker attendance because we need it to be entered as a parameter. And we'll say if worker attendance is greater than or equal to 0 and worker attendance is less than or equal to 100, then we're going to say attendance equals worker attendance. Finished.